Okay, and we are live. So welcome everyone to today's live science session, and we are continuing with the trend of working on infrageometry. So today we're joined by Carlos, Nick, and myself, James. And Carlos is basically going to give us he's going to give us, how would you describe it, Carlos? What is the agenda? I'll let you describe it.
Yeah, so today we are going to go wide instead of deep, I guess.
Okay.
Many of the past streams we were focusing on getting some of the concepts right, and I think it's and as many people saw last time, we were struggling with just finding directions. So we are now taking a complementary strategy. We're just going to go as wide as possible within all the scope of differential geometry. So I prepared sort of a summary of concepts and ideas that make differential geometry as a mathematical discipline. And I'll present this, I'll try to explain without getting into any of the specific details, but just to have a broad perspective, what things look like. And then hopefully we can try and see how we react and how our intuitions match to some of the proposed analogs in infrageometry, because I've essentially gone trigger happy with just guessing and just throwing some plausible implementations in infrageometry for a lot of things that we have no like formal verification or any kind of evidence that things are working. So yeah, hopefully that'll be something useful for both the audience to see and for ourselves to kind of get some larger perspective.
Okay, so taking the analogy of exploring the terrain, we kind of took a very specific path. We traversed the depths of the jungle to try to see if there's a way through to this correspondence, which is kind of the ultimate goal maybe for this current stage. And now we kind of like surveying the land a little bit and making sure that what are all the options, what are the suggestions. So just taking like a kind of a broader look of, we're putting our head up for a while. So there's these periods where you have to put your head down, grind through the details, and the other periods where you have to look up and say, okay, are we still heading in the right direction? What other options might look more fruitful, something like that.
That's right.
Cool.
That's about right.
Okay, and then so you're going to explain everything, and I guess you'll start also with the direction, like why the why question, basically. What is the goal as well?
Yes. Should I start sharing and then we can go there?
Yeah, let's do it.
Wait, let me just pause this thing here. I'll keep an eye on screen sharing this. I guess you can see that.
Yeah. Let's just check the zooms. Can we go zoom in a bit, maybe 150 or 125?
Yeah. That better?
Yeah, that looks good. Okay, yeah, everything looks good.
All right, so just to recap very briefly, when working with infrageometry, the main goal is to provide sort of an orthogonal approach to why hypergraphs are the good objects to consider in finding alternative foundations for physical theories. So one of the strategies that we decided to follow was to try and take hypergraphs as a starting point to develop a mathematical theory or a computational mathematical framework that will essentially recover differential geometry or resemble differential geometry sufficiently that we can practically use it in modeling. So as I said, we in the last few past live streams, we've been trying to really nail down some of the core concepts of differential geometry. And we had some strong intuitions for some, Nick had a very nice idea to consider multiplicity counts to bring some numbers in an automatic, natural way out of multi-hypergraphs. But beyond the very basic intuitions and the very basic definitions, we haven't found much success just noticing whether there's something like differential geometry going on in this system. I would say that the main reason for this is likely to be that we really don't know what the framework should be yet, meaning we don't exactly know what we are looking for. Because I would say we are not looking for a mathematical theory in the conventional sense of the term, meaning we are not looking for something that you can just summarize in more or less standard terms of category theory or set theory and just package, write a paper, and communicate it. I mean, we can certainly write papers in that vein about the framework, but that's not going to capture the framework. And so that's part of the difficulty. My background is in mathematics. And that would be the natural thing to produce, to sort of program in the language of mathematics, in maybe the more set theoretic version of it, or the more categorical version of it, but certainly programming in mathematics. And here we're programming a little bit differently. We want to see if we can be sort of hypergraph natives, and we can do everything within a hypergraph world where we're basically considering computers that just might have some familiar architecture, but otherwise only perform hypergraph transformation operations. And those are essentially hypergraph rewriting operations, as many of you are probably familiar with. So, so the plan for today is twofold. First, I'm going to show you basically how I conceptualize differential geometry as a field, and sort of all manner of keywords and concepts and how things are dependent, more or less. And this will be a very good reference for the future when we, I've said many times in the past, the directional derivative is very crucial because this enables this and that and all those things. So I tried to map this out actually using our hypergraph packlet for visualization. So I think it's already a pretty nice application of this functionality to do on a mathematical notebook. I think this was actually not possible before we had the packlet, so it's already pretty nice. And then hopefully in the second half of the live stream, we can all brainstorm and see if we can come up with some concrete implementations, concrete examples of the things that I propose. So does that sound like a plan? Is everyone?
Yeah, that sounds good. Maybe if we can just touch on quickly the connection to the bigger why question here with regards to does this kind of fall under like a physics project? Does this fall under tools with which to explore the Rulliad? Is that like a decent way to describe kind of a potentially bigger goal?
So infrageometry, I would say, I mean, you'll see there are some interesting points of contact with different parts of things that are going on at the Institute. So there will be a moment where observer theory becomes relevant, I think, and there will be a time when things look very mathematical and all about sort of algebraic structures and higher or infra mathematics in some sense, things that are not quite mathematical structures, but are nonetheless emulating them in some regime and things like that. But yeah, in some sense, this is like, although it was motivated by the physics project and by saying, okay, physics project seems to be doing well with hypergraphs, and maybe we can take hypergraphs as primitive objects and just try to do mathematics with them and just sort of instantiate our mathematics directly with hypergraphs. This is more like an attempt to run mathematics, a familiar area of mathematics like differential geometry, and try to sort of bring it up or spot it in a very unfamiliar computational setup, right? Because the familiar setup is that of, whatever formal language in which you're implementing your set theory or your algebra, and then you construct the typical definitions of topology and real analysis and all those things in that computational framework. We're trying to do something quite different here. We are trying to implement hopefully eventually those notions in particular, but we're implementing sort of more parsimonious notions that might map into those eventually. So in a sense, it's like trying to recover particular mathematical objects within a formal language that is just hypergraph rewriting. And it's very simple hypergraph rewriting and very sort of minimalistic hypergraph rewriting, which is everything begins with some undirected multi-hypergraph, and we try to see what naturally arises from there. Also, I see a comment on the chat. Yes, we will make this notebook available, especially this differential geometry section, because it contains a lot of the useful information. So we can keep an eye on. If you're not on our Discord server, be sure to join there, and that's where you will find all the posted notebooks.
Great. We also had a question from Perpetual Science early on. I guess it was left there. Should we leave that till the end, maybe after we got into infrageometry specifically?
I can see that. That's too specific to address early on. So
okay.
All right. So my summary of differential geometry is largely based on a book that I personally didn't use to learn differential geometry, but I've consulted a few times, and I know it's a very standard reference. This is Lee's Introduction to Smooth Manifolds. So look, you can see the outline of the book here. It has all the usual stuff. Now, a keyword selection. This is also one of Stephen's asks that would just take a bunch, like 20, 25 terms that we definitely want to be able to capture somehow in our framework. So these are some very familiar ones: topological space, chart, as in coordinate chart, manifold, function, cotangent bundle, curve, tangent bundle, smooth map, differential of a map, also known as the differential or the tangent map, for those of you who are familiar, submanifold, one parameter group, vector fields, flows, Lie brackets, cotangent bundle, exterior derivatives, differential forms, tensor bundle, metric volume form, integration, Stokes' theorem, vector bundle, principal bundle, and Lie groups or Lie points. So these are essentially all the, if you know all these objects and we can work with these objects, I would say you definitely have recovered differential geometry pretty much in full. So how do these things come together as and how are they articulated? So let's have a look at this particular diagram. So this is how I would summarize differential geometry as a branch of mathematics, right? So you see there's a area here for algebra, there's an area for topology, there's an area for real analysis, and differential geometry is something that is genuinely new out of these. So it's none of these three areas that have a very long mathematical tradition behind them, and extremely well-funded theories, and some of them are at the very foundation at the very core of mathematical history. But differential geometry really gives some new concepts. I've selected 6 to just highlight sort of 6 sufficiently novel notions that it's not easy to find analogs in other mathematical theories. Of course, under the optics of category theory, you will say, well, where the role of the form integral in differential geometry is analogous to the dual pairing of algebras and blah, blah, blah. It's like, sure, but you need some machinery to make that analogy. So the 6 concepts I'm highlighting there is some choice. Is not particularly exhaustive or anything, but it's some choice of core concepts that are genuine to differential geometry. So things that kind of what differential geometry purchases you. So whenever you make the effort to construct smooth manifolds and all the machinery that comes with them, these are the things that you can do that you previously couldn't do, right? Basically in other, or not very easily in other mathematical theories. So you can see here from algebra, we'll have the notion of ring. The notion of ring is essentially the notion of scalars, numbers, things that you have your real numbers or your rational numbers or your complex numbers. A Lie bracket is something that people very familiar with the algebras and fundamental physics will be aware that of the importance of the Lie bracket. A graded complex, this is a very technical term, but this is the one I chose to choose just because it is everywhere in differential geometry. So a graded complex is essentially just a bunch of modules or vector spaces that have normally some operation that sort of change them in a certain way. So the example in differential geometry is the exterior algebra of forms. So for those of you familiar, you have functions, and the differential takes you to one forms, and then the exterior derivative takes you to two forms, and so on. So you have this D operator that changes from spaces of forms, right? So that's essentially the idea. And then, of course, derivation, which is the interaction of a linear map with a multiplicative structure of a ring in a very specific way, so that it satisfies the Leibniz rule, so the product rule of derivations. So that's the algebra side. On the topology side, of course, you need, so that's all well and good in the algebra side. On the topology side, you need the notion of space, right? So the notion of space, what's most relevant for geometry would be the notion of connectivity, meaning where things are and how they are connected. The notion of path, which is a specific kind of connectedness, but a very important one, because differential geometry was mostly developed because of physics, and obviously physics is all about trajectories and particles moving and things like that. So paths are extremely important. Of course, continuity, which is in a sense the backdrop to where most of the spatial things happen. If you recognize something as being spatial, we probably are thinking of something that is continuous to some degree, because that's how we understand space. We feel that we are embedded in some continuous regime of our surroundings. And then finally, the notion of manifold. So the notion of manifold is, some people normally only hear this word in the context of differential geometry or even general relativity or something like that. But the concept of manifold is quite a specific notion within topology, which is could be captured as the general idea that you have a model space, something that you know fairly well, or you have a very good machinery for, and then you want to understand some more complicated space. And what you're going to do is you're going to say, well, at every simplifying patch of my complicated space, which could be, the idea that on every neighborhood of a topological space, you might find a mapping that is somehow telling you how to navigate that particular patch, because you have a model space, because that mapping tells you that patch looks like your model space, right? So typically, this is what the idea of coordinates are, right? Like if you have a sphere, you can, place your favorite coordinate charts, whatever you want. Like, if you are on planet Earth, you can define your longitude and latitude, or you can look at a cardinal point and measure the angle and have some chart that makes sense. You look at maps are oriented in every which other way, and you have your coordinates and maps, and those are all good for navigation, right? If a map is well made, it doesn't matter how you chose the coordinates, it's going to help you with navigation, and that's the point. So that concept is topological. That is the notion of topology. And that is sort of the main contribution from topology to differential geometry. And then finally, of course, is real analysis. I mean, topology and algebra, in a sense, don't speak infinitary in some sense. They are perfectly well defined without any reference to the continuum, to the real numbers, right? And so we need to bring in the real numbers, because the real numbers is our model for how the geometry around us behaves. If you think about the history of real numbers, that's where they came from, right? When we needed some numbers that were not rational, it's because we were trying to measure the diagonal of a square, or we're doing something that was spatially interesting, like drawing a circle, right? So that's why we need real analysis. The most important notions from real analysis, I would say, are, well, integration and differentiation, of course, bringing calculus from the 17th century into a higher mathematical construction, but also very crucially, the notion of distance and order. I only included distance just for simplicity, but the notion of order, the fact that 7 is less than 11, or that pi is less than 2e, right? These relations are very important, and the way the real numbers interact with distance and order, so how you multiply things, you add things, divide by things, and so on, and how those things interact with the distance is what makes everything tick. I mean, if you think about it, when you define limits, when you define continuity of real functions, when you define differentiability of real functions, and you develop all your theory of calculus in a modern sense, you will be using consistently this idea of distance, right? It's all about comparing whether two terms differ by this amount, and controlling that amount and all that stuff, right? So when all these things come together, the algebraic part, so you are ready to abstract quickly and to package some complicated, potentially complicated geometric notions into simple algebraic packages. When you bring topology that gives you this tool to represent space and connectivity and how things relate in a broad locus manner, and you bring all this machinery from the geniuses of the Leibniz and the Newtons that taught you how to integrate and to differentiate, you put them together and you get differential geometry. That's essentially the discipline that we are trying to recap here in infrageometry. So I chose these 6 concepts. So what I like to do next is to basically show you some definitional dependence of these things. So just to exercise a little bit the complexity of what's behind here, and also to note what are, if we go to the roots of these DAGs here, you will probably find the places where we need to really focus on building intuition, or trying to somehow find the infrageometric analogs, right? So, for example, in the case of smooth manifold, you need, so a smooth manifold, I mean, it's easier to read the diagram actually top to bottom, and the direction dependence is, the edge relation here in this graph is essentially definition is used in, right? So in the definition of a smooth manifold chart, the definition of chart is used. The definition of topological space is used. And that's kind of how you construct these graphs. I made these graphs by hand. I mean, it would be great to have some kind of automated, mathematical repository that just, you can pull this out. But this I just made with our hypergraph backlit. You can see I can edit, I can, like things around a little to make them, a bit more easy to read. I'm just gonna collapse, yeah. Oh, well. So anyway, so for example, smooth manifold, we can see that we need, so a smooth manifold is a topological space with a collection of charts, right? And these charts need to be compatible, but a chart in turn will need reference to some kind of model space, which in differential geometry typically is not just a generic affine space, it's typically a concrete affine space. It's usually Rn for some finite n, where R is just the real numbers. And then, of course, to define a chart, you need the notion of a continuous map, which means that you need to know how to map between topological spaces. And to know how to map between topological spaces, of course, you need to know how to map at all between sets, right? Which sounds very trivial, but in our infrageometry project, this is a big problem. I mean, it's not obvious what maps should be in our context. I mean, there's a naive option for that, but I think it's not the end of story. And then if you don't take that route, then it's a bit more complicated. And then, of course, you need to define topological space. So topological space, you need a set of things to begin with, some set of points or locations. And then in that set, you need to define what an open set means, basically just to give an idea of locus. So you have this dependence. Similarly, for directional derivative, we'll have to understand the notion of differentiation in general, this idea of rate of change in an abstract sense, in a general sense, that comes into the notion of directional derivative. But then more concretely, as I discussed in past live streams, you need fundamentally the notion of a curve and the notion of a function. And as long as these are defined locally at the places where these things are defined, you will be able to get a directional derivative if these things are successfully implemented and everything is working fine. So a function essentially just requires the notion of local values, something that we can, assign as a local property of your space. And the curve essentially, needs to live in a topological space, because, I mean, thinking of curves in something that is not looking like a topological space can be a little bit spurious, although probably for our case, that's not going to be an issue because everything is going to be finite and it's hard to tell when things are going to resemble topological spaces in a formal sense. Right. Oh, sorry, I have copied the same thing twice. I just noticed here. Why is that the case? What am I missing?
There's 6.
Principal bundle. Yeah, missing principal bundle. In a second. I think I have it in a different notebook.
So some of these things are connected, like topological space. Well, I mean, they're the same. So you could even have like a connected map where these things go in different directions. Maybe, right?
What do you mean?
Like affine spaces in smooth manifolds and curvature tensors. Or where was it now? Sorry, formal integral. Yeah, so they could be connected. Like could have like one big map here potentially.
Oh, absolutely. I mean, this is this is just a sketch, some kind of sketch or cartoon of just to make a point. But of course, this is sort of the sort of dependency structure of any mathematical theory, right? You're going to have, but in this case, it's completely focused on definitions and constructions, right? So just to, because our system is very constructive, right? We have ways of constructing hypergraphs or notions within hypergraphs and protocols, so to speak, to give it a very vague name. So for some kind of hypergraph protocols, kind of combination of algorithms and sort of algebraic notions kind of mixed in. So those protocols will correspond hopefully to some kind of constructions in mathematics. So these diagrams are expressing constructions. So of course, all these notions require the definition of a smooth manifold, and therefore all this, that diagram is in all these other diagrams. And every time you're talking about, so I try to emphasize the things that are sort of specific to those constructions, right? So yeah, anyway, next one is principal bundle. Principal bundles are the mathematical tool that you need to essentially do modern particle physics. These are where gauge theories are formulated. And most physicists today would agree that they are the nice mathematical object to capture symmetry, fundamental symmetry in nature, the way we've observing it in many different ways. And they seem to be very good to also quantize and then get all the nice particle physics and the fundamental interactions out of them. So just as reference, the standard model is formulated as a quantization of principal bundle theories, so gauge theories on principal bundles. That's why I chose this particular object. So yeah, for that, we need notions of transformations of our space, invertible transformations of our space. So that obviously evokes the notion of a group. And I put OID in brackets because we definitely don't want to be demanding totality of our operations because we are in this finite setting. So groupoids are probably our best friends in this discrete context. Another interesting concept is the tangent functor. So the tangent functor is a fancy name to describe that whenever you have a manifold, you can canonically construct its tangent bundle, basically just the bunch of tangent spaces glued at every point of that manifold. And it's called a functor because the construction respects essentially all the structure that you have in your smooth manifold. And the output is a smooth manifold, right? So a tangent bundle is itself a smooth manifold of double the dimension of your original manifold. And when you make the construction and you have any sort of notions you have smooth maps between manifolds. You take the tangent construction and the differential map between those, you get exactly a homeomorphic mapping of those notions. So that's why we call it a functor. So obviously the crucial thing there is to understand what is a tangent bundle, what is a tangent vector to begin with. Directional derivatives are needed for the definition of the differential map. So you normally model the differential map after what you do with directional derivatives. And then a couple more things that to get more sort of physical in a sense, to get closer to physics, or at least classical physics. Principal bundles were more for high energy physics. These two are more for GR. So form integral is the generalization of the idea of integral, and I call it a form integral just to make clear, differential form integral. And this is the notion that given a K form, you can integrate it over any K-dimensional submanifold of your space. So a K form is some kind of tensor field on your manifold. So the idea is that these objects are essentially dual to submanifolds of your space, and then the integration process is essentially a dual pairing between these two notions. So in order to get that working, you need for sure the notion of a chart, because we are in manifolds. And then the reason I remind the notion of chart here is because you need oriented charts. So you need the notion of orientation, which is something that doesn't come for free in a vector space. When you choose a basis on a vector space, you might have wondered at times, okay, the statement about a basis, if you remember what a basis is, given a space, a basis is a number of elements that will allow you to express any other element of that space as some linear combination. So essentially a weighted sum of those elements, right? So for finite dimensional vector spaces, that means that you will have finitely many such elements, right? So you might think, okay, so normally, well, not normally, but addition is commutative and associative, meaning there's no order between, when you specify a sequence of basis elements, there's no particular order there. But very often everyone signifies that the basis elements are ordered in some sense. This is basis element 1, basis element 2, basis element 3, or ijk vectors in 3D and so on. So the choice of such an ordering of basis elements it corresponds to an orientation, is what we call an orientation. We basically give some kind of handedness to the space. It gives some kind of chirality, asymmetry to the space, and the idea is that your basis could be in this orientation or it could be in this orientation, and these two things are inequivalent, right? They are not the same. I can put one on top of the other. They are essentially different, and the difference between these two is that I just flip one of the vectors. One of the vectors, I minus it, and I get the other one. Right? So orientations are this kind of concept. So that is crucial to define what a volume form means, which is in a sense a concept that is defined purely in terms of linear algebra. But then if you have your notion of cotangent bundle, which is another thing that we are struggling to find, then you can simply extend the notion of volume form all over your manifold, and that will allow you to define, with the help of the notion of integration that will come probably from real analysis, or maybe the notion of line integral in a manifold, which in turn will come from the notion of directional derivative, you will get to define this general form integral. And finally, curvature tensor. This is perhaps the most iconic, almost object that people relate to differential geometry. I mean, I'm happy to bet that anyone who's heard of differential geometry in any capacity, classical differential geometry, modern differential geometry, more abstract, they have dealt with curvature tensors, or they've sort of had curvature tensors as some kind of end goal, sort of goalpost where you approach in order to define, all the necessary machinery. So curvature tensor obviously is defined from a metric tensor, but it is an interesting object to consider as kind of a goalpost, because it requires the notion of the natural notions that derive from metric, like geodesics and parallel transport, but it also requires the notion of tensor bundle generally in your manifold. So it requires the fact that you're building these towers of objects on top. And of course, those things require tangent space, which is another fundamental object. So anyway, this to me is a good map to. I don't know if someone in chat or any of you two guys have any comments, or I don't know, maybe discrepancy
about the integration part.
Yeah.
Do you think like the the fundamental target would there be like describing the generalized Stokes theorem, like what it, that all this means, like integrating differential forms,
Definitely.
and there's would be some kind of discrete version of that.
I mean, I don't know if I can show you maybe the other notebook. I think I erased it, but I actually had Stokes' theorem as the item instead of form integral first. So you're absolutely right. But I decided not to have Stokes' theorem just because I wanted only constructions and not results. Because the Stokes' theorem is a statement about boundary manifolds, right? So the manifolds with boundary and forms in some space, right? So I wanted to just list the objects that you require to form the statements. Obviously, the most important statement will be Stokes' theorem. I would completely agree. We want some kind of discrete version of Stokes' theorem. That's the end goal. If you have that for something that you can identify as the metric volume form for some kind of Riemannian structure or infra-Riemannian in our sense or whatever, I would say that's job done. We've done it. If we have that reliably and we can convince some other mathematicians that actually, yes, there seems to be some kind of infra Stokes' theorem going on there, I would say we are done.
So what do you think personally? Like the nature of the Stokes theorem, as I remember it, it's like it connects the notion of boundary with the differential. And we struggled to define the differential thing. Maybe if we manage to define what the boundary means, maybe we can use it somehow.
Oh, I see. Uh-huh. Oh, that's a very good point. Oh, always Nick with a timely, insightful comment. Yes, no, that's right. Okay. That's a very good point. Yes. So as a reminder, I'll just show this for a second. So the next thing here is a complete list of all the terms that technically we will need to go through. So instead of just having this very scary list, I try to divide it in some sort of sub-domains of topics. And you will see here that, where is it? Stokes' theorem is down here. So the idea of Stokes' theorem is that you have a notion of integration, which I think everyone is probably very familiar with because you learn in high school how to integrate, and then you can easily imagine that you generalize, the area below a curve, you can generalize as the sort of the volume of the corresponding geometric shape, lengths, areas, volumes, hypervolumes, whatever. Right? That's essentially what integrals do. So the idea is Stokes' theorem essentially relates or makes an equivalence between the differential operation of forms, which are some kinds of tensor fields, which essentially generalize the notion of taking a function which is a zero form, taking its differential that it takes to a one form, which is the differential. It's a covector field, and the operation which means to take the boundary of a submanifold. You take a submanifold like a path with two endpoints. The boundary operator on that thing is a new submanifold, which is just the two endpoints, right? If you have a torus that is closed in space and like a surface, and you take the boundary operator on that, you will get the empty set. So it has no boundary. But if you take something like a cylinder with two tips, and it's an actual cylinder, it's not like it's not closed. You take the boundary will be two disjoint circles, right? And so on. So that's the idea. But those two things are embedded surfaces or embedded manifolds, right? One is a sort of looks like a sheet with some kind of cylindrical shape. The other is two circles in space. And what Stokes' theorem that tells you is that if you want to know how a form integrates some kind of information about the bulk of the shape, so the inside of the cylinder, or the surface of the cylinder, you can reduce to computing an integral along the boundary, so along the two circles. And the kind of information that you integrate in both places, one has to be the differential of the bulk, right? So you think of the infinitesimal as being the differential, right? And this is indeed a generalization of the fundamental theorem of calculus. If you go all the way back to high school, when you first learned that integrals are antiderivatives, but the process of integration can invert the process of differentiation. And so if you have a function of which you only know the derivative, you can actually know the values of that function by computing the integral of that, right? So the idea is that you integrate a function from a to b, and if that function is the antiderivative of something, then you're going to get just the values on a and on b. So basically, summary: either evaluate at the boundary or integrate the bulk with a differential expression, right? So that's that's Stokes' theorem. I don't know if there's a quick, Nick, do you know a quick way to like make Mathematica write out Stokes' theorem, or like is it in some kind of?
No, maybe
We'll just paste it from Wikipedia or something.
Oh, you mean just the notation for that?
Yeah, just the notation. Yeah, just the notation.
Or just request you to type the integrals, right? Or maybe the boundary thing.
Yeah, well, that stuff is a little bit heavy to. I'll just copy from Wikipedia. I just want to.
There's a writing assistant. I'm pretty sure there's some symbols there for.
Okay. No, I just wanted to copy very quickly. I don't want to spend much time, so just.
Yeah. Just.
We have some comments in the chat. Maybe I'll just read those out in the meantime. So Perpetual Sounds was saying, have you guys looked into Regge calculus? Regge. It's like discrete GR differential geometry. Then there was, you can make non-orientable and non-parallelizable orientable and parallelizable by adding compact spaces. Okay, I'm gonna have to try to read that again to make it make sense.
Yeah, I'm just bringing.
We get it's like a comment about the Regge calculus. It's like I personally haven't like learned it, but I know its existence. Yeah, it's a like discrete version for general relativity. You can formulate it there.
That resolution is terrible. Let me see if I can. Yeah, but anyway, this is essentially the shape of Stokes' theorem. So you can see that to know what happens. So this curly d on omega, on big omega here, is a boundary operator. Big omega will be some submanifold, and small omega will be some differential form. So the shape of this theorem is basically telling you if you want to know how some object integrates along the boundary of a region omega, all you have to do is integrate the differential of that object in the bulk of that region, right? So it's a theorem that allows to translate between bulk information to boundary information by computing a particular operation, which is the differential operation, right? So obviously the main statement of the theorem, many people have seen a lot of theorems like this before in school, because I apologize for the resolution because I think, let me see if I can make it. Oh, yeah, it's going to be better. So a lot of people would have seen this kind of theorem in high school, right? Where you have your boundary terms are so your region omega is just an interval in the real line, with endpoints A and B, and so evaluating the function at the endpoints just gives you this particular value, and which is an oriented value, meaning that you actually compute a difference, and then to get that value, the computed value, you need to integrate the bulk. So do something in the entirety of the interval, which is this integral construction, but you do it for the derivative of the function, not for the function itself, right? So generalized Stokes' theorem captures this, but also captures a lot of the theorems that people probably dread in in undergrad courses in physics. Beautiful Green's theorem or Gauss's theorem. So this is what is called Stokes' theorem in 3D, because that's due to him. That's what he actually did. And let's see. So yeah, this is Gauss's theorem. I think that's another formula for familiar. Oh, come on.
Yeah, Perpetual Science reworded that tongue twister I tried earlier. So what he was actually saying here was a two-sphere is not parallelizable, but a two-sphere product with a one-sphere is.
Oh, let me see that question. A two-sphere is not parallelizable, I agree, but a two-sphere product with a one-sphere is. Yep, that's right. I think it's a bit advanced for our purposes here. Parallelizability has to do with whether you can describe the tangent bundle of a manifold as a trivial bundle, but which is essentially whether you can comb a hair on the manifold without kinks in some sense. And you know, when you add an extra, when you times a sphere, so clearly you can do that on a sphere, right? Imagine a hairy ball, you can comb that without kinks. But then when you times it with another object, basically you thicken it, you make it three-dimensional, even though it's still kind of round because it's a Cartesian with another round shape, and a circle is one. There's enough room for the hair to sort of arrange itself in a way that you can no longer have kinks, right? Or sorry, you can comb in a way without that leaves no kinks, right? So anyway, so these are the theorems that people might be familiar with. This is the generalized one. It's absolutely true that we want to get this. And so the next comment was to say, well, if we are struggling with the differential construction, which we are in some sense, I mean, if we knew how to take the differential of a function, then we will basically know how to take directional derivatives. And so Nick was suggesting that maybe we look at the other side of it. So we think of the boundary operator as a stand-in for our differential operator. So just to give a summary of what things we seem to have some agreement on. I mean, you can see that some of this is the total list. We shouldn't look at that. Some of these lists are quite populated. Some others are completely empty, right? And most of these terms here are guesses. These are some kind of trigger-happy guesses that don't really correspond to having checked what we have there. But if we review very quickly, normally we think of differential geometry as being built on top of topology. So we first need some base topological space, and then we assume further things on top of that topological space. So we begin with a point set, which is basically just a set. There's our set of points that our topological space is made of. We are thinking of it as the vertex set, but I would say also the place set, meaning place, remember, is the combination of the edges, so the edge places. Now, open sets and closed sets, this is the language of topology. My sense is that we don't want to necessarily recover explicitly topology in a direct sense, because you can always do that with finite sets. And other than that construction, I don't see a reason why you should do this. But open sets are essentially regions of your space. So if we're thinking of our place set as the collection of locations, then a region is going to be some subset of those things. Or more generally, a sub-hypergraph. If we have a good notion of sub-hypergraph, then probably these are that. Whatever the notion of open set is, the easiest way to define an open set is to say that the easiest way to define a closed set, once we have a notion of open set, is to say that the complement of an it's the property of a complement of an open set, right? So basically, you take your hypergraph, you take whatever you define as an open set, and then you subtract And subtraction here basically means the inverse of the additive union operation of hypergraphs that we have. So again, something that can be defined with rewriting, with some reductive rule or something like that. It seems likely that if we have an open set notion, then closed set shouldn't be that difficult. Topological space, the intuition is that it should be some kind of skeletal hypergraph, meaning simple, meaning that multiplicities are collapsed and all those extra features are sort of smoothed out, probably without self loops or something like that. Although maybe that's just not so important, but some kind of notion that just basically determines connectivity patterns between places. What a continuous map is, I honestly have no idea what that should be. I think, and let me explain why I think this is complicated. So in principle, if you have a mathematical mindset, there's no such a big issue with considering continuous maps. If you're happy with what you call a topological space in this setting, and we have some class of hypergraphs that we are confident are capturing the notion of topological space, then it should be fairly straightforward to say, let's consider a kind of hypergraph morphisms, which are maps between the sets of vertices and the sets of edges that respect the structure of a hypergraph, that further respect whatever makes the hypergraph a topological space, right? So that's the easy route to define maps in the infrageometry setup, but I think that's just not good enough. I think that's because that's essentially a notion in mathematics that's not implemented with rewriting at all. That's some kind of extra data structure that you put on top of your hypergraphs, right? You're basically saying, I can construct this map object, this kind of map type on top of my hypergraph type, right? And that might be fine. That might be okay. That we could be okay with that, but it does break a little with the philosophy of just being sort of hypergraph natives and just doing hypergraph operations all along. So my idea for a map, or continuous or smooth or whatever property you want to attach to it, is to, the closest thing to a map in the context of hypergraph rewriting is confluent rewriting, right? When you begin with a single state and then you have a confluent rewriting system, right? Remember, confluent means that you have one final terminal state of your rewriting. So effectively, you can encapsulate, you can sort of contract all the middle operations because you always get to the same place, right? So maybe that's the notion that we want, and so maps could be confluent rewritings of a given state. But of course, this differs substantially from the notion of map in mathematics because it is totally state dependent. The same rewrite rules will be confluent on some states but on others, right? And obviously it is rule dependent. So there is this sort of more vacuous nature to confluent rewriting that is much more, what's the word? It's much more nuanced than, say, I have hypergraph A mapped to hypergraph B, right? So yeah, but I think that's really the only, I don't know if you guys can think of something else that comes to mind when thinking about something like a map, or indeed anyone in chat. Any ideas, Nick? Or what could be a map in this context?
Didn't we mention something like a function at one stage? Like function maps one thing onto another thing?
Yeah. But this is somehow more fundamental in a way, because so
map
functions
itself.
Yeah. So functions are particular in mathematics. Functions are particular kinds of maps. They are mapping from a space to some value set, some number set, or some ring or something.
Or just rules, like nothing from besides the rules comes to mind.
Well, but the rule does not define a map, right? In general.
Well,
a rule application.
What's required Was it required? What is required to be a map?
So if you have, okay, let me put it this way. Imagine you have a universe of hypergraphs, right? Bunch of hypergraphs. And you take a rewrite rule. Then that rewrite rule, imagine it, and the universe of hypergraphs where that rewrite rule applies. It's just a population of hypergraphs where that rewrite rule applies in some way. Then, okay, actually, forget that. It's just the universe of hypergraphs, right? The point is, when you define rule application in a mathematical sense, you get a partial, but not so important, map from that universe of hypergraphs onto itself, right? Because given an element, I will check my rule application, and then I will perform one of the rule applications, and I will get an output that is another element of that same universe, right? So that's the relation of the notion of rewrite rule with the mathematical notion of map. But a single rewrite rule and a single state is not mathematically equivalent to a map, right? Because it's just one single object to another object. And here what we're trying to, and there's...
But it describes the rewriting, right? So you can apply your rule to a single hypergraph, which is like an instance of your hypergraph domain.
Sure.
Yeah, so you map it to another hypergraph. So it's if you assume that it's like a single way, you can do it like in a single way. So it's like a single valued function. But in general, it is a multi-way because there are multiple ways you can apply this rule.
Yes.
And even functions can be multi-valued, like in complex analysis. So,
yes. I'm not worried about multi-valued. I'm worried about the locality nature of rewriting. So a map, I mean, I'm not saying that we have an issue with the notion of process or
like a fixed point. It's local, but you assume that you run it until you stop applying it. It's like
but that's why I'm saying but that's what I'm saying. My candidate definition is confluent rewriting, not rewriting in general.
Yeah. That's not confluent, but maybe normal, or what is it? Coating. Is that the point that you have like a normal hypergraph that you rewrite all your inputs, right? So the rule is basically always have a fixed point in a way.
But I think my point is, so the analogy that we're trying to build here between continuous map or map, to be honest, and something here, right? Map needs to, so the equivalence works as well, right? We have point set to be the place set already, right? So the hypergraph already, right? The full hypergraph is the point set. The analogy is that a continuous map takes every point in the point set to some other point, right? So if the analogy is that the entire point set is a single hypergraph, one hypergraph, right? Which is the whole game of infrageometry, then I would say that the requirement for the map really is confluence and not just termination, right? Because you want a single output of your as a result of your rewriting. You see what I mean?
We just said that multi-value doesn't matter.
No, multi-value is fine in general to consider for rewriting or for other purposes, but to capture map, I think it's bad because it's not a map, right?
So it's yes. So that's what confluence basically means. You have a single output. Right. And it has to be like fixed in a way.
Yes. So, Okay, so then I was just checking that we agreed when confluent rewrites is a good candidate for mapping, right?
Yeah.
Okay, good. So
are those lists of candidates? So vertex.
Yeah, these are a list of candidates. Yes, these are all candidates. Yeah, maybe for the people joining. I see Angelo's memes. Welcome to the live stream. These on the left, we have some technical objects, concepts, constructions in differential geometry, separated by some sort of domains like algebra, more topology, more conventional differential geometry, more Riemannian geometry. And on the right, we have the candidate constructions that we are thinking about from our investigations in infrageometry. So yeah, so
Do
we
we
just
have-
said that map. Yeah,
Oh, sorry,
go on.
we're going to finish this one. There's another one I wanted to ask about.
Yeah, go ahead.
No, I wanted to know where path was. Is there a simple just path by itself, like path groupoid, or is there like a mathematical?
You mean this correspondence?
Yeah, I guess a curve is the same as a path.
Not exactly. I mean, we are distinguishing the terms just for the sake of accuracy in a sense. So curve. So this was one of the most intuitive things that we've, especially since we decided on the place graph.
So that was our word for it. Path.
Yes. So it's more than that. So actually, this is what we already had here that I can show, which is in paths and curves. So they are different things in our setting. So my current understanding of these, so we are now in our conventional infrageometric setting for those following in this familiar territory. We have some spatial graph, looks like that. I mean, ignore the ugly labels just for reference here. A path, the way I mean, we can decide different convention, but the convention I've chosen here is a sequence of this kind, right? So it's a sequence of edge, vertex, edge, vertex, edge, vertex, right? So if you put it in the bigger graph, which we now very conveniently can do just with addition, you will see that this path is going through this 12, this edge, which is E12, 15, then this vertex 15, then this edge, which is 4, blah, 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 and so on. A curve is an integrated path. So it's the net vertex place sequence, right? So the curve integrating, or a curve integrating this path is, for example, this one, which is just 12 directed 15, directed 9, directed 8, but also just 12 directed 8. That's also a curve in this sense, right? So I'm not super attached to, obviously, to these terms, the path and curve. We just need two different ones because these are different notions. A path will always be like an actual path. That's why I call it path, like an actual graph path. This is what people call paths in graph theory. And the curve, I'm calling something that is a little bit more abstract in your space because it's an integrated trouble in your space, right? So the integrated trouble might have different layers of granularity, and it is defined to be only defined on vertices, right? So yeah. Anyway, okay. So what is? Oh yeah, here we are. So yeah, so the analog of a curve, then we are thinking of a directed to edge sequence in both the notion of path and, I mean, this idea of path in the place graph, right? That's what we just showed, path in the place graph. Nick, do you have any worries or considerations at the level of curves and paths?
Well, I'm thinking right now, like, what would be the difference? What is the usual difference between like Riemannian and Lorentzian manifolds, and how curves are different there? Do you have to distinguish them?
Not at the level of
property.
But they are only distinguished. I mean, they can be distinguished at the level of curves, right? A curve in a Lorentzian manifold and a curve in a Riemannian manifold are defined the same way, but the metrics on the manifolds see them different, right?
Mm-hmm.
I mean, this gets a little bit philosophical because, differential geometry always has its philosophical kind of side. I had just as an anecdote, I had my sort of a dissertation advisor in Cambridge actually was a philosopher of general relativity. And he was very insisting that there was confusion in the mathematical community about whether intrinsic points of a manifold were ever actually the subject of our inquiry because we only have coordinates to refer to them and things like that. So there is some degree of philosophy that goes into this, but mathematically speaking, you as an object, as a mathematical object, a curve is is indistinguishable both in Riemannian and Lorentzian, because the way that people typically define things is just modular, right? So the module that has to do with the metric geometry doesn't really interact with the module with the. I mean, it interacts, but it doesn't depend, right? You define things like distance of a length of a curve, angle between curves and things like that when they intersect and things like that. But they don't influence the way you define them, right? Of course, you do get like a more physical interpretation. You get things like classification of curves, and then upon a classification of curves, you can define things like the affine parameter of a curve. So you have things like a canonical parameterization of a curve. Normally, a curve doesn't have a canonical parameterization because you can always reparameterize your sort of mapping from the reals to the manifold, and that's the same curve geometrically, but a different curve in terms of parameterization. So the tangent vector will be different, right? So in Riemannian geometry, you have a way to canonically parameterize all curves, just period. But in Lorentzian geometry, it depends whether the curve actually is time-like, space-like, or no, right? So that's, you can see a difference, but it's really in this extra layer on top of definition of curve, right? A curve is normally given as a parameterization, but a lot of mathematicians think of curves as the equivalence class of all parameterizations, that blah, 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 blah. So.
I see. Yeah.
Could a curve be thought of as the shortest path in the place graph between two vertices?
So, okay. So let me address that point. So that would be something that we might want to consider as some kind of canonical metric structure on our hypergraphs. Obviously, in the places graph, there will be such thing as minimal distance paths, right? Because things are going to be finite and discrete, so this is going to happen. The game here, I think, should be, and this will be interesting to what degree that canonical metric structure on a graph is going to interact or is going to be relevant to describe the geometric notion of metric in our sense, sort of inframetric to distinguish the other. But my intuition is that we should not be somehow like lured by that, because it is there for free. But the way we're thinking of these hypergraphs is that the actual distances should be kind of irrelevant. And I hope that this helps clarify sort of some people watching and our own understanding. The idea is that many different hypergraphs will be able to capture the same geometry, right? So you could have vastly different distances, like numerically, but you might be capturing the same geometry, which is incidentally, by the way, where I just mentioned about parameterizations of curves, right? You can reparameterize a curve and geometrically nothing changes, which is the same idea that you can change your chart of coordinates, you can express everything completely differently and nothing changes geometrically, right? So because we might...
What is hypergraph? Is it like a representation of sort? What do you mean by it's like different hypergraphs can encode the same geometry?
Yeah, this is where I was going to when, where is this? In topology, yeah, in the chart part. So I don't know, but imagine, okay, let me make this clear. So in a topological space, right, the information of a topological space really has no bearing on how many points there are in your space, and to be more precise, the size of your sets. Like you have volumes or you have distances defined or things like that. Topology doesn't care about distance. Topology doesn't care about size, right? So if you were to argue that you are recovering a infra topology, right? So some kind of infrageometric, hypergraphic that recovers geometry, then in some sense, the amount of points, meaning the amount of edges and vertices in your hypergraph, shouldn't be that important, right? It shouldn't, I mean, obviously it's going to be important in a specific case for the things that are defined, but you would probably want to capture things that don't depend on that, because it's the same thing as saying, you know, what is a sphere? Sphere, you can represent it in many different ways. And you can, in particular, take your favorite three-dimensional space, and you have infinitely many embeddings of spheres. All of them are good enough to do calculations about spheres, right? So this is kind of the philosophy that I'm thinking about, that if we are going to capture something that we call topological or geometric about hypergraphs, they, even though a particular calculation, a particular algorithm, or let me call it, what did I say earlier, a protocol, just to be a little bit vague, a particular protocol that we apply to a hypergraph, it obviously will crucially depend on sizes and length and whatnot. But the statements that are made about dependencies of different hypergraphs with that protocol and so on should probably be independent of specifics. So I'm saying this very vaguely. I don't know exactly how that's going to work. For the time being, I'm thinking much more as static hypergraphs. So a hypergraph is static. So maybe let me explain what I meant, because this is really the juiciest correspondence in the entire list I made, is this one, because it calls back to something that's kind of observer-based descriptions, and this might be actually an interesting point of intersection between what we're thinking about for observers in a causal sense, and here might be some kind of static observer kind of idea. So what I'm thinking about this is the idea of model space, right? In conventional geometry, you have a manifold is really a patchwork of charts, right? You have some base set, and that base set can be, in fact, you can not even assume that that's a topological space. It can be just a kind of a random set, doesn't matter. But if you have an atlas structure in it, which is called an atlas, which is a collection of charts, which effectively is a patchwork, something that covers the whole thing with open sets that have non-empty intersection. And so it covers the whole thing, and on the intersections, they agree. And agreeing is a very specific technical statement that we don't need to spend so much time right now, but agreeing means that there is this ambiguity that you can, you know, given one description of a point or a structure locally in your manifold, you can change to a range of other possible descriptions. So in this hypergraph setting, in my view, we have two choices. Again, the easy one, the sort of cop-out, you know, like just the model, just take an embedding of a hypergraph, you know, just a mathematical notion of mapping of a model hypergraph into a hypergraph, into a larger hypergraph, and you say, okay, given that that's effectively your coordinate space, so your model hypergraph could be like labeled, could have all manner of like metrics defined on it. It can have all kinds of things very predefined, or you could even have a family of such hypergraphs in some sense. And then you go on your hypergraph and you basically just pattern match and you just, you know, glue it everywhere. And so your hypergraph is made out of those, right? And that's an interesting concept to think about, just in terms of, you know, a hypergraph that has the property that you find a small hypergraph that has some kind of symmetry or some kind of internal structure, and you say, the property of this bigger hypergraph is that I can find hypergraph embeddings that are overlapping everywhere. And, you know, the overall structure can be complicated, but the local structure, I can always call back to this. I think that's too much on the nose analogy with coordinates, in my opinion. It's interesting to consider, but I think it's too much on the nose. My other suggestion, my other idea is doing something that feels more like observer-based, right? So basically, we only have access to rewriting. So what we are going to consider as a chart is possibly some kind of sub-hypergraph that effectively gives you a domain. So some kind of open set, right? That might be, but open set might be even like an open ball, right? Where you place at a vertex and you say, go up to distance, whatever, or something like that, right? So you just define some open, some region of your hypergraph, which is some sub-hypergraph. But then what you do there, you don't just mathematical embedding whatever and match vertex by vertex, edge by edge. but you do some kind of rewriting procedure that just applies rewrites locally to that sub-hypergraph. And then we say some kind of, we put some kind of conditions on rewriting, like you have to be confluent for this or that, or you have to always end in this, with these rules, always with this final state. But that's, I think, a good way to summarize, one example to summarize that, which is something I want to formalize a little bit for tomorrow with Stephen. So that's the idea that I'm thinking about for charts, that you might want to say every time you match with what we could call a neighborhood, that's a more neutral term that it doesn't evoke so much topology like OpenSet, but we could say neighborhood is some sub-hypergraph or some designation of a sub-region of your places graph. And then you say within there, apply these rewrite rules. And the condition is that you have maybe a confluent system that always outputs whatever, like this particular hypergraph or something isomorphic to this particular hypergraph, something like that. I don't know. And so that is a property. I mean, that certainly constrains what kind of hypergraphs you can have. Not all hypergraphs are manifolds, given that. Now, the question is whether that is going to do any work for us at all to like define things in terms of.
Are you basically trying to define what the hypergraph version of the manifold is based like relative to a rule, which is like an observer that tries to, when he tries to rewrite some local property of it, sub hypergraph, it's actually, I don't know, always maps to the same thing. So if you like can partition your hypergraph so that this particular rule has this behavior, so that it's like always rewrites this particular open set maybe to some fixed value, that's basically defines a manifold. Because you also automatically have some notion of the open set that behaves in some way nicely by the under this rewriting rule, because that's the only operation we can do, as you said.
Yeah, that's kind of the idea. So the one picture I have in mind. So imagine an extremely regular hypergraph in the sense that not technically regular, also technically regular, but constant degree, constant arity. So like imagine like a 3 uniform degree 6 hypergraph, which is basically like a tiling. It's like a surface, like it's a triangulation of the plane, right? So if you have that, you can quite easily define something like, rewrite 3 triangles to make a larger triangle so it matches the tiling, and you want to somehow so it matches the triangulation, and you want to somehow say whichever region you get, you always get something confluent to the triangulation of that set of vertices, right? So a triangulated surface on that set of vertices. That's what I would say, right? So that's kind of like saying, I get this crumbled up, given a set of vertices with edges, get this sort of messy thing, and I apply some rules until what I get is exactly a triangulated surface on those vertices, which it looks like this very two-dimensional manifold in this case, right? It looks like locally like a plane. For this particular observer. So that would be true for all observers. So meaning that partially they have to overlap. They can, the original sort of match, the pattern match will have some symmetry because it can be rotated or whatever. So I think that, my intuition is that constrains what kind of hypergraphs you can define a lot.
Well, imagine also, like again, like your example of the triangulated mesh, right?
Yeah.
Your rewriting is to rewrite a triangle with just fine-grained version of it, and you can do it indefinitely. So it's basically your rule doesn't have to hold. In this sense, you kind of can fine-grain all of your triangles, and it doesn't change the nature of your original mesh that you started with.
It doesn't change the what? Sorry,
So it's the mesh. So you defined your surface by triangulation. So you just fine grain each individual triangle, each polygon by just dividing it into more pieces. And if you apply your procedure to the same triangle multiple times, you don't have to stop, right? In a way, don't change some global property of this hypergraph.
Sure. Yeah, we maybe want some confluent or some, maybe not confluent, but at least terminating procedure. Because if we're doing things like in this finitary approach, we might need to, I mean, if it's, yeah.
Well, can you define something like using this infinite recursive function that rewrites any hyperedge with multiple hyperedges that preserves the original connection, but it becomes more and more fine-grained in the process?
So you mean adding new vertices?
Sure, yes. It's like basically what you do in any numerical relativity stuff, I imagine, trying to solve some differential equations on your space-time manifold. You start with some initial data, and if there's some more action happening at that particular point, you try to fine-grain it in order to improve your accuracy of your computation there, right? So in a way, continuity can be defined in this way, right? You don't have to go all the way to the limit, taking an infinity limit of that process, but just specify that it in principle can be done up to any degree of accuracy.
Yeah, no, that's interesting. I mean, my intuition is going in the opposite direction, in that, so not in the opposite as in like thinking that that's wrong, but in the opposite of, I will think of more reductive rules for charts, just because I'm thinking of confluence as being like, I don't know, maybe some throw statement out there could be like, mathematics is confluent rewrites or something. I don't know. Like it might sound like too crude to say, but you know, that's exactly what you miss. That's exactly what you lose when you do these multi-way things, right? That you are no longer single valued, and you can no longer just begin a process, end a process, and just, you know, connect a nice, tag a nice morphism to it. It's like, okay, A morphism, B, deal with it, next thing. Like that's what we lose in this situation where things are local, things are partially defined, and so on. And that's why I'm constantly thinking, if the idea is that in some Ruliad Platonic sense, all these things are happening in some computational universe, in some distant, faraway region of the computational universe, and us as computational observers, as sort of human beings with our limited minds, we really like mathematics. We've invented mathematics as this way of really capturing the patterns that are relevant to us. To me, it seems that confluence seems to bring out the mathematical nature, or the mathematical flavor of these kinds of constructions, and that's why we kept going back to these kinds of things where, like the notion of addition of functions. I mean, I think I have it down here, like what we discussed last time. Yeah, like actually, this rule here, right, to implement the Hadamard product of functions that we discussed last time, it's neat because it is going to be terminating, and it's going to be confluent, right? Given a hypergraph that is labeled with two labels, or I mean a graph in this case, just to use this rule, right? If you apply this rule, it's going to look at all the combinatorics, and because things are getting relabeled, so the pattern match no longer works. you are going to get a confluent system. So this process that is defined here as just multiplicity, right? In here, it's just multiplying. This is, by the way, this is just a cartoon. It's just typed there. It's not defined. But this is how it works, right? Like it does this, and it also multiplies multiplicities locally. You can get that, which this is a mathematical operation. It's just defined globally. It's just one go, input, input, output, boom. It's an operation. It's a mathematical operation. But in a rewriting sense, you can apply this thing with the caveat that you need this labeling thing that, you know, that's part of the architecture, kind of the computer architecture. That's why I call it a protocol and not an algorithm. It's some kind of, it's a little bit more vague, but it does rely solely for the process. It relies solely on pattern matching and output in a multi-way system, right? So it's not deterministic in the usual sense. It's not single output in the first instance. But if you let the system run until it dies, you will get the inert state in the end. That is the actual output of the multiplication here, right? With the correct multiplicities and everything. So, in my view, that's like we had to be clever to like set up our rewrite system in this kind of more or less complicated way, so that we could pick out a mathematical structure, a mathematical operation, something that we understand as, oh yeah, you can collapse all the intermediate steps and it's just this times that, and that's how it works, right? So that's kind of the general philosophy that I have in mind. And for those operations, things need to be reductive, right? They need to be, because we want termination, we want confluence in many cases, we want this kinds of things. We want like, but anyway, but your intuition is also interesting, that we might want to have this idea of refinement or like levels of accuracy or refinement or something like that. So yeah. Anyway, that's the main. I mean, there are many other things that we could discuss. I mean, all these things are initial guesses, but they are all based on this idea. So it's not like I am missing out like 2 hours of discussion by not mentioning those. They're all based on this idea of trying to implement. Maybe what we're missing is the implementation of charts. Maybe that's what makes geometry in some sense. I mean, that is true. I mean, if we were to capture something about geometry in a single sentence, it would be something like, geometry is that thing that happens when you change and it doesn't change or something. You know, like it's this kind of this very abstract notion of geometry as invariant, transformation invariant, and so on. And here, the thing that changes in differential geometry is exactly chart representation. And some people might call it like diffeomorphism invariance and things like that. But really, I think the correct notion is chart, because the chart diffeomorphism is a mapping from a space onto itself, and that's a little bit too self-referential for what we want. And here, very much the idea that you can define. There's a definition of manifold that you can do without topological space. So you can begin simply with set, as I said earlier, and then use a definition of chart that is it's a little bit more refined than that of it. Obviously, you can define a chart as a homeomorphism from an open set of Rn to an open set of a topological space, which is normally how people define it. But you can simply define it as an invertible map from a subset of your Rn to a set, to your manifold set, to your point set. And if you give enough structure to the overlapping conditions, basically saying that they are indeed homeomorphisms of Rn and so on, or diffeomorphisms of Rn and so on, you actually induce the notion of manifold, and you recover the definition of manifold. So, in that spirit, I think it's worth possibly exploring the idea that you have a hypergraph that you're thinking as your space will be very complicated, but you are going to define manifold hypergraphs as those that have some behavior under considering this sort of local observer sort of perspective, which is this idea of a local chart graph. And again, if you're very naive coming from mathematics, you would try to think of something like just take something that is an embedding of a sub-hypergraph and that can be mapped in every other way around the hypergraph. I think we should not do that. We should stay true to our approach on using rewrite rules and do something that is, yeah. Anyway, that's what I said before. I was just emphasizing the point.
Is there other interesting expansions of the groups below, of those subsections below, that we can go into, or we're going to save those for another time? Below the tables, there was individual sections in the notebook.
Oh, these ones you mean?
Yeah.
So these are the sections that we've shown before. So there's not much new going on here. We probably want to create something like for later, where we try to instantiate what charts look like. But yeah, I mean, this is basically, and you know, the whole business that we've been thinking about, you know, where you have a tangent graph that looks like this, you know, given a special hypergraph, you have some directed edges on top of it, and you're thinking of that as your tangent graph. The idea, of course, is that everything you implement is rewriting on these things, right? So that's kind of a difficulty that we're sort of, except for possibly some specific cases, we are out of proofs, right? It's going to be difficult to prove stuff in a sense. We will have to be guided by some intuition, and we'll have to say, yeah, this rewrite rule seems that it's going to do the job for this kind of thing, and then we will apply it and see, okay, this happens to be confluent and happens to capture what we want. And even as I said originally, even the definition of these hypergraphs from the original hypergraph, I mean, I hope everyone agrees that this, for example, the places graph as a construction is again it's a confluent rewrite system, right? Did I include some of these functions here? I don't think I did. No. But yeah, so basically, but I think it's obvious, right? So if I have my special hypergraph, which looks like this, right? To create the places hypergraph, I just need to create new vertices that remember which edges they come from. So I can just directly create new edges on top of that look exactly like this, right? So if you think what's happening here is a focus, for example, on the leftmost edge over here, right? That is a ternary edge in the original special hypergraph. So I'm going to have a battery of rules that can apply anywhere on my hypergraph, and they're going to pattern match for edges of a specific arity. And depending on the arity, the pattern that is going to be replaced is going to be add a new vertex and then draw some directed edges from each vertex to that new vertex, right? And the number of edges equals the number of the arity of the edge, right? So with that, that's a battery that's a tower of potentially infinitely many rules, but you know, up to the maximum arity of your hypergraph, what people call the rank of your hypergraph, right? So that's a finite amount of rules that you apply to your system. That's going to have a nice multi-way sort of behavior, but it's clearly going to be confluent, right? Because it's going to output this thing, this single hypergraph in the end, right? So to me, and this is maybe a narrative I'm building now to comfort myself, to feel like I'm making some progress, but I'll say it anyway. To me, this feels like if we are thinking that this kind of looks like a tangent graph that kind of is behaving kind of like a tangent bundle kind of thing, to me, it feels like we are forcing this infra world of just rewrite rules into behaving like mathematics, like human mathematics, right? We're forcing it because the way we specify the rules to be kind of more or less sensitive to the initial state, right? We are forcing them to, and the fact that they are sort of like one edge to many edges and just has only one new vertex is created, and the output creates a pattern that no longer can be matched by the rule itself. Right? That's a way to understand what's going on here. Basically, the output of the rule never matches again, right? So you don't have this sort of interesting causality phenomena that you have in other systems that for other reasons we absolutely want, right? But for these kinds of situations where we want to be more mathematics-like, you might want these kinds of things, which are, reducible. I mean, this is not done by the rewriting in the code right now. This is just done by some function here. You can see, right? It's some mathematical code that does the thing. So you can imagine that, the internal stuff that Mathematica does is kind of equivalent to some set of rewrite rules that is operating. And in fact, Mathematica is rewriting based, so it's very accurate in some sense, in some technical sense, that this is a single output, right? It's a well-defined single output. So yeah, that's
what if the places graph is the fundamental graph and there's a way to just represent it with a hypergraph? So it's not.
Say that again. Say that again.
No, I'm saying what you're suggesting there is that there's a way to go from the hypergraph to the places graph using rewrite rules. Or was it a different statement you're making?
No, that's exactly what I'm
saying. So maybe one way to look at it is that this places graph is the fundamental representation of the information. Like you don't need to adjust it. The hypergraph is just like a higher order representation of a bipartite graph. Like this, like what you're seeing here is the foundation. This is the basis.
Well, it doesn't matter, right? I mean, we all know that hypergraphs are the same as labeled bipartite graphs, and undirected hypergraphs, that is. Right? So, that equivalence is there mathematically, but if our fundamental object is an unlabeled hypergraph, because space, I don't know, space doesn't seem to carry labels. Right? Like
so the labeling part is what you're saying is currently being like something we're adding to it.
Yeah, the color here is representing a label.
Yeah, okay. So I see what you mean. So
you can remove the notion of label when you construct the actual, for example, this tangent, what I call the positive tangent graph, right? Because then things are labeled by the structure of the graph, right? Like nodes or vertex places are only have tails, and edge places only have heads, right? So that particular pattern of edge place versus vertex place can be captured by this particular hypergraphic structure, right? If you just do this, obviously you need labeling. If you just do the actual, what we're calling the places graph, which is this undirected binary graph, you definitely need labels, because otherwise, there's no way to tell how this is a hypergraph, right? And we are of course taking hypergraphs as our base object for granted. Like this is like there's no debate that we are doing that, which I think is pretty natural, because they are just combinatorial objects, and it's very minimal. So all these constructions are basically as minimal as it gets when it comes to computational processes. I wonder if I see. So Brady asked, is the multi-way structure thrown away then, or is there a place for it besides within map? So if I understand that question, because I read the question a bit earlier. So the multi-way structure is not thrown away. I hope that it became clear with what I said in the last 10 minutes or so, that we are thinking of the multi-way structure as something that, if we are clever enough, we will tame, and things will get confluent, and then it will look mathematical, it would look operational. But in general, the framework doesn't assume it, right? So the framework is, lives in weird territories in Rullial space, in the computational universe. Like these kinds of constructions are very weird, right? But in some sense, one could argue that the kind of construction that you get when in differential geometry you have a manifold, which is some amount of data, and then you pick a point that automatically generates, say, the tangent vector space at that point. A vector space is a different kind of object than a manifold. It's a different kind of object than the point. They are all made of sets, and they are, in some sense, in substance, they are similar, but they are not considered subsets of a larger set in any sense. To me, all these things are analogs with what we are doing here, right? Like we take an edge, like that triangle in the background, that spider webby looking triangle, and then we replace it or draw on top this set of three arrows to the middle vertex, right? I mean, again, it's a hypergraph. It's a kind of hypergraph. It's a directed hypergraph made of vertices. Like it's to me, it's analogous, right? There's a degree of formal analogy that is super high level. It's not formal analogy in any other sense, but it is a formal analogy in the sense that you have two objects that are generating two other objects of a similar nature in the same framework that can interact with each other, right? So you in conventional differential geometry, you can interact between a vector and a point by saying, oh, if I have a curve through that point, maybe that vector is tangent to that curve or not, and so on. And in our setting, we have hyperedges on top of vertices, and because we have rewrite rules, they can interact, so they can generate some other structures with these things. It is just the case that we need to be very sort of clever with our rewrite rule selection to make these things speak and to have them, which is the exactly analogous situation to usual mathematics, right? You need to be very clever to choose your axioms and to choose your definitions, so your mathematical system does work for you, right? Like it does something at all. So anyway, I mean, again, I think I'm sounding more hopeful, just not to go back to the pit of despair that was last session, where was very little insight on how we are progressing here. But I think that it is necessary pains, because this is a very weird setup for a human mind in a way, right? So it's a very different way of thinking. Evangelos' negative base number systems are constructing non-standard positional number system. So is that a reference to choosing some clever axioms or some clever constructions to aid you in further developments, if I understood correctly? Yeah. So Nick, what do you think, or how do you think observer theory, the notions that we're thinking there, apply here? Like how? Because obviously I'm thinking of this notion of observer as some kind of mathematical observer that is just checking some kind of phenomena within some region. But do you think it could make sense to maybe even like think of a notion of an observer on each chart and think causally within each chart? Because in some sense, but just to rephrase the question, confluence is some kind of extremely strong causal property, right? It's like a super strong causal constraint. So maybe some weaker constraints for observers might be more relevant, or more general constructions that are still understandable, I guess.
Well, Well, that's when I think like the notion of the difference between Lorentzian manifold comes in. It's like you have to know what is this causality direction. It's like if you just pick an arbitrary hypergraph and you subgraph, if you define some subgraph as an observer, then defining some properties relative to that subgraph is not clear unless there's some notion of what is the interaction between that pieces. Well, you can compute some static things, right? Just relative to this thing, like a distance, average distance to that other part. But in terms of rewriting, it's kind of too weird. You can even maybe imagine that there's like the subgraph itself acts as a rule. It's like self-applying hypergraph of sorts.
Yeah.
It's like if you imagine an observer being just a part of the hypergraph itself and it acts as a rule, how would you just apply that subgraph to the other regions? And you can define that this is how, in principle, the interactions of an observer with the hypergraph around it.
But I think the key here, the key idea here would be the interaction between two charts, right? So, and that's where I think observer theory might be most relevant because on the overlap, imagine that observers, charts are defined as this loose sense of like two hypergraph regions, meaning some sets of edges. So essentially two sub-hypergraphs, and they have non-empty intersection. On that intersection, the two observers are going to apply. So they will have like different rules or whatever, how we define different observers. And so the idea is like on that intersection, there's going to be like some kind of interaction between observers, right? So it's the idea maybe we'll have to put some constraint to say those two observers actually are observing the same space, right? So that puts constraints on the space, the spatial hypergraph that we have in the first place, and it puts constraints on what are observers, valid observers for in this sense, valid charts. But that's exactly what we want. That's the whole point. But I don't know how to define. I mean, it's just in my head that's purely conceptual. I don't have like a good example of what would be like a condition to like how two different observers interact.
Well, in a way, the writing itself defines the direction, right? So
Sure.
if you have a static hypergraph and you apply a rule by one observer, you get one evolution of this hypergraph. If you apply a rule corresponding to another observer, you get another evolution. But the point, the direction is already defined, and whether they agree that there is an evolution corresponds to the same universe they perceive, that then you can just like immediately jump to the causal graph description and talking about in those terms.
Yes.
And of actual individual events of rewriting and their causal connections.
Yes.
Right? And whether they correspond to one or another observer. So it kind of makes more natural than thinking of just a single state evolving relative
for sure.
Right?
No, exactly. And I mean, I think I can draw here. Right? Let's see. If I just annotate here, you guys can see it, I guess. I have to unshare for a second. Actually, I'm just going to start a whiteboard briefly. So what I have in mind is you have your hypergraph over here. You have your hypergraph over here, right? And then you have some chart over here. You have some other chart over here. And there's so each chart, in some sense, it's going to be some kind of rewrite system, right? It's going to flow, right? Same here. This is going to, this is going to flow, right? So this intersection over here is going to look like I have some hypergraphic structure on top of the thing, wherever, and then I'm going to rewrite with two possible, with a green rewrite or with a purple rewrite, right? And then, and so it's going to be this this double causal system. Right? It's going to have two kinds of rewrites.
Yes, it's a multi-way causal system. It's a multi-way causal graph.
No, but yes, but no. But what I mean is that it's going to be several purple ones and several green ones, right? These are from two different observers, right?
Sure. Yeah.
And then the idea would be, in my opinion, to try and like characterize something that somehow is common among the two, some kind of property between the two observers. This doesn't make any sense.
I think it's just causal invariance again.
Which
just like
means,
which means I think it's defined like that you have the causal graphs are isomorphic, but it's not necessarily.
Yeah, but you agree that this seems that there could have something interesting in it, right? Like there could be some way to systematically say, these things are going to do complicated stuff, but they need to, on the overlap where they both apply, they need to interact in some way that is, some causally characterized way between the two, right?
Well, sure. If you just abstractly think in terms of events, if they agree, it's fine. It's like a single way causal graph, no ambiguity of rewriting happens in terms of like relative to any of those two observers.
You mean it's a situation where like when you have a state like this and then it just both rules give the same.
Yeah, if you have like both rules and you assign those rules to two observers, right? And right,
Yeah.
you prescribe the rules themselves, like as an observer, so that as one individual rule defines the evolution of one observer.
That's right.
Starting from some particular chart.
That's right. Yeah.
Right. So those two. So it's not contradicts like any other notions. Like we could have like defined the whole evolution of our Wolfram physics, Wolfram models, having two rules, two hypergraphic writing rules. Just now assign them to two different observers, and we just talk about them in the same terms. If the rules can overlap, on acting like in some ambiguous way to some specific hypergraph region, then it's like that's where ambiguity happens. That's you necessarily have to branch and consider two copies of the hypergraph now. Essentially, right?
Yeah.
So that's where the multi-way system, basically emerges, and the multi-way causal graph in particular, because if you don't have any ambiguity, it's just a single evolution. You can evolve like under in any order you can apply those events. They always produce the same thing. This is just a pure single.
Oh, I see. Okay, I think, okay, so let me make sure that I'm getting the core point here, which is you're saying that, because I was implying that these things were labeled somehow, that you had two different causal ways, but you're essentially saying that on the overlap.
No, events are labeled. So your arrows here in the causal graph, they would be events. You just label them by what particular rule you applied. So we label each event by an observer. And that's how essentially what I've been doing with like with chains.
Yes.
We have a way to label them with one specific rule, for example.
Yes. No, I understand. What I mean is that I was thinking that they were going to be labeled beyond just being by the rules, in the sense that if the rules were shared, they could still be different. So, but I see what you're saying. So essentially, And it is great because it means that the overlaps need not be binary or anything. We don't have to care about the number of observers that are coinciding there. You're basically creating a multi-observer, right? Which is aggregate all the rewrite rules together, right? And then that's a new rewrite system, right? A rewrite system is any collection of rules, right? So you begin with the ones from A, A here, observer A, observer B, right? So A and B have their sets of rewrite rules and they create their sort of rewriting cones, to speak. And then when you, on the sets that they overlap, they create this sort of A intersect B observer, which has the combination of both rules, right? It's just a new observer. And maybe it's as simple as saying that observer needs to have some kind of property, some causal property. Maybe we just say confluence. Who knows, right?
So what I don't like about assigning rules to observers is that it makes them non-local in a way, or even you can imagine a situation when one rule can apply but another can't, right? So it's observers just, or they may iterate. So you have a state when only one single rule can apply to one particular. So basically, your observers keep taking roles, whatever.
Yeah.
Kind of weird. And
can you elaborate a little bit? What makes it weird?
Yeah.
Well, it makes them non-local in a way. If you imagine just the colored causal graph, right? Causal graph is colored based on rule is the observer, so you basically immediately assign the whole regions of the space-time to different observers. Globally.
So wait. So, but remember, I was bringing in observers only for the compatibility condition part, but I would still define a chart as a sub-hypergraph. So that's where locality comes from, and a set of rules, right? Which is what you do in geometry, right? You have a open set where your chart applies and the actual assignment of coordinates, which would be the process of rewriting by the rules in our setting.
All right.
Right. So
if your set of rules is global and the same, doesn't have to be, then you can as well define the chart just by the region itself.
Sure, but then I don't. Yeah, I guess that would be a particular case.
It's your structure already dictates how the evolution is going to happen. You don't have to prescribe some different rules to that evolution.
Well, I'm not sure because
maybe you can imagine that your actual rules, global rules, are universal, like universal Turing machine, and the region itself prescribes how you turn this universal, using this meta universal rule, into any arbitrary rule, right? By the actual initial condition. So you don't have to prescribe any rules to that particular evolution then.
Yeah. Yeah, I don't know. I mean, maybe I'm limited because I am still thinking in terms of trying to be analogous to a chart. So just specifying a domain. Although there should be the yeah.
Well, you can define a chart by this recursion of again taking some universal global rule that can produce a chart by just applying to your initial condition, with this discrete subregion of the hypergraph. You just take it and you imagine that the rule that just applies and expands it to the whole nice Euclidean space. But it only works on a region, like a small one. Because if you apply it to some large region, is gonna, I don't know, introduce some weird
I
geometry.
understand, but isn't that what I said earlier, that you have like a rule and a hypergraph with a region that satisfies the property that you just apply the rule, and you get a confluent final state that looks like maybe some regular thing, some triangulation or something.
Well, that's the confluent thing in that case, your Euclidean space, right? That's what we try to, right?
Yeah, well, I mean, sure.
And the analogy is
The analogy would be yes. The analogy would be yes, the Euclidean space. But my point is that the Euclidean space is in a geometric chart in differential geometry. The model space, the Euclidean space, is constant, and what changes is the domain where it applies, the open set, and the mapping, obviously, right? Like the mapping, and the mapping can change without the domain changing. That's this sort of diffeomorphism invariance kind of thing, or where the way that
your evolution to this final state, which is the analogous to Euclidean space, has to basically take those points on the hypergraph to the same thing, right? That's how you can. So that's your gluing condition essentially. It's not just the same thing. You can define your open sets not as the regions of hypergraph that evolve to the same final state, but also the gluing condition also evolves some particular points to the same one that are in the intersection of those regions. So you have to have this ability to track some particular vertex or place, a place through this evolution.
That I understand what you're saying, but that seems hellish to implement practice.
Well, in practice, yeah, but well, conceptually, we were just doing the definitions today.
Yeah. No, I mean, I understand, but like, because I think in practice what we want, I mean, I don't know that, and Stephen was also mentioning that we probably want things that are like that we somehow the simplicity is in the conditions, and the complexity is in the process, in some sense.
Oh wow!
Like, and so meaning something like you reduce you reduce the notion of chart compatibility to simply the statement that, oh, the rewrite system that you get on the overlap is confluent or has this one causal property, whatever it is, right? Instead of, and the causal property might be it is confluent to a hypergraph in this family of hypergraphs, which might be this idea of a Euclidean space, right? So triangulations of the plane are a family of hypergraphs, right? So,
well, you kind of can define this gluing in some evolution that not happens like independently on those patches. You can evolve the two patches that intersect, or define it in a way that the evolution has this property when you, for every pairwise intersected regions, they evolve nicely, or just confluent or whatever. Don't have any ambiguity under this evolution.
Right. Yeah, this could be. It's interesting because I was just thinking of something interesting. Actually, I just thought of something. I mean, it's not to update anything we were saying, but kind of to conceptually wrap up things kind of nicely here. See how we were thinking about rewriting rules and all these things as the way to do infrageometry, it might be that all those rules actually all apply locally, and that's what a chart is, right? And that's actually very conceptually accurate to what differential geometry does normally, right? Because as I said, your manifold set is this sort of abstract world that you don't really, like in some sense, epistemologically, you don't really have access to, right? You only have access to the things that you can compare on it and things like that. You know, like when you have things on it and you put a chart, then you can start to get things out of it, right? Because you see them in your chart and you understand your chart. So all the things that we mentioned before, like multiplicity counts coming from some rewrite rule, paths, meaning that you can rewrite the tangent graph in these ways, you know, all those things obviously apply if you say you have to restrict to this particular chart, to this particular sub-hypergraph, right? So it might be that observers are just what we're calling infrageometry, sorry, charts are essentially observers carrying the infrageometry ideas to a hypergraph where they live in some sense, right?
Wait, say
I'm
it
not
again?
saying it. Yeah. I'm not really contradicting anything that we said before. It's mainly just we were describing observers. Sorry, we were describing charts as this idea that they are kind of observers set on some sub hypergraph, and we were thinking some abstract view. Maybe they carry some rules. Are there rules? Blah 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 blah. But then what I thought is, wait, but we needed a lot of rules already to make the whole thing function, right? And because we're not thinking that we have to generate these hypergraphs. These are God-given. This was one of the main premises of infrageometry, that they are God-given. We begin with a potentially very complicated hypergraph, and we're going to do something on it. We're going to try and analyze and get something. What you do on it to do geometry is to throw charts at it. And then you constrain the charts that you can throw at it by saying that on the overlaps, you need all these compatibility conditions. So I think all the things that we discussed in the way of rewrite rules to implement geometry-like objects and algebra-like objects should actually go to each of these, should effectively become the sort of mathematical observer that are bound to a chart, a particular chart, right? Because so things like, you know, multiplicities of edges, right? The multiplicity, like as a reality check, multiplicities we can measure by confluent systems and just measuring the causal distance, right? Because you just apply at every edge, you reduce the duplicates, and the number of counts in each of the edges gives you the multiplicity count. That is obviously independent of observer, right? Because that rule is going to be the same for all observers, because every observer is going to look at multiplicities in the same way, because it's the same rule. But if you had something that transforms somehow, it depends. Like those are intrinsic properties. It's like you know, a function. The value of a function doesn't transform in a coordinate transformation, right? That's the analogous thing I'm saying here. Like the function at a point has a value. An observer sees that value, and any other observer will see the same value at the same point. You don't have to transform anything. So in our framework, that means that the same rule is applied by both observers. That's why they see the same value, right? That's kind of reason. But there might be other properties that are observer dependent, which could be the idea that your manifold locally looks like this space, right? That is going to be observer dependent, probably, right? Because I don't know, if you have to, if it looks like this space means two different things. I mean, you can be the same space in two different ways, right? Like, there can be isomorphism in several ways. So those will be different, and then they mix in the same rewrite system, and then you might want to say there's some causal compatibility or something. I don't know, but my point is that all the things that we were considering earlier perfectly match here by saying you don't need some kind of weird computing architecture where you have like rules that are kept in some kind of memory outside of the hypergraph or anything. Those are actually the things that define charts. you put those things as a package then, and you define the domain of application of those packages. And those are effectively mathematical observers of that domain of the hypergraph, right? Yeah, I don't know. I'm seeing this picture as having some potential, some interesting structure. Because what we were lacking before was structure. We were just completely structureless. We knew how to rewrite. We could define any rewrites we wanted, but we were completely structureless. This gives us a little bit more structure. It doesn't give us a lot, but it does give us a little bit extra things to start, like maybe trying to illustrate some basic notions. Like, we should probably think of very simple systems like one-dimensional hypergraphs, right? Like just chains of nodes. Try to think of like rewrite rules are essentially just concatenating nodes and see, these kinds of, and see if things make sense in those settings.
I agree. I was just struck by something Nick said earlier, where you were saying that there's maybe challenges with thinking about a rule as an observer. And then I was like, because of the non-locality thing, but there's nothing to say that observers are local necessarily either. And just thinking through this idea of like a specific rule is just a specific observer, but there's many observers that are very similar. And where you apply the rule on the hypergraph determines what happens to the hypergraph, but similarly, what happens to the hypergraph affects how the rule could be applied as well. So there's kind of like this interaction between the rule and the observer and the hypergraph. So you could constrain an observer to act in a specific part of the hypergraph depending on how the hypergraph, depending on the information in the hypergraph. But you don't have to either. So I just thought this was like an interesting idea. And in terms of maybe as a prelude to tomorrow, some quantum effects that might have, where you have three different observers, each with their own rules, and how those could interfere and interact with each other might be quite interesting to explore. So I don't know, it's an interesting concept to think about, that an observer is not necessarily a node that's persistent over updates, but is the thing that is doing the update in itself.
Yeah, this has to be. Yeah, I mean, an observer is going to be some structure of a causal multi-way system. Right? I mean that.
Yeah.
In a way, you could even think of it in a much more mundane sense, and you can call these computational observers, like I think Stephen has called them again sometime before, in the sense that you have a domain of application, meaning you're gonna ingest some data that is not infinite, so that's why you need to have some sort of local domain, and then maybe you want it to be connected because that's kind of what spatial means in some sense, and then you're going to have some computing power, right? So that computing power is your rules, right? Like that's the things that you are going to do, and you have many rules, then you have more computing power in some sense. If you have fewer rules, it's not exact, but it's kind of that sense. And then you're going to take that, you're going to process, and the causal structure of the rule application to that domain is, in my view, entirely analogous to the running of computation. Right? You just process data, and you're processing data. You go here, then I can go to these other places, and the causal properties of that characterize how you characterize the data, right? Because characterize, under the light of this observer with these apparatus, you're going to get this causal structure. With these different apparatus, meaning change some of your rules, you're going to get a different causal structure, right? And if you even can look at the states themselves, you not only look at the causal structure, you can say more things, but even just at the local structure level, you can say some very parsimonious statements. Right?
So you could say something like where an observer applies, where an observation rule applies, or like finds a chart that ends up being confluent, then that is something to say about the hypergraph. So we have these spaces here. Oh, it's going to get a bit like, say there's a specific rule that only applies to this area, and then every time the rule applies, it kind of like has this situation, and it could be making the thing confluent to a point, like maybe multiplicity, where there's only one thing that you can talk about. And then there's a different rule maybe that applies to this section of the hypergraph here. And okay, the intersections could be something different, but they'd say that transforms into like a skeletal representation of that, sub hypergraph over there. And you can almost say like through each iteration, this is a rule that is applied to its observation. So you can almost say like the observer is the thing that's charting, that is doing the charting of the hypergraph through rule applications.
Yeah, that's essentially the picture, yes. Just to reply to Dugan in the chat, Dugan says, in my mind, an observer is pinned to a location in the hypergraph, and it receives photons from its immediate surrounding, and it is the photons which are moved about the hypergraph via rewriting rules.
Yeah, that's the other way to look at it. That's like maybe the opposite way. It's like an observer, something in the hypergraph, and rules like affecting it. What was interesting is just the thought experiment of inverting that.
So I think, well, there's something that doesn't quite match for us. So if you were to think of, I mean, in a sense, there's only hypergraph. So photons need to be made of hypergraph as well, right? So in a sense, there's only one substance, and that's hypergraph, right? So photons you might want to characterize with something like unary edges that are flying around or something, but the whole idea here is that we are really trying to mimic differential geometry, right? We're really trying to mimic charts in topology. So we want to have this notion that something applies to a region of the hypergraph, some kind of computation applies there, and that's what we mean by ingesting information. You compute, quote unquote, compute the dimension, things like that, compute multiplicities of functions, all those things you do by applying rewrite rules. And then if you have the overlap of two or more of that, you need a compatibility condition. You need a sense in which these are observers of the same universe, and they are coinciding on some region of that universe. And so yeah, maybe it's inescapable that we were kind of already hinting at the fact that we were using the causality properties of rewriting systems as a way to encode many of the mathematical structures here, but we now seem to have it almost inescapable that we'll have to do that, because in a sense, geometry is based on locality, and that's what geometry, classical differential geometry, that's essentially what it does. It encodes this idea of local behaviors, right? Local functions, local curves, local phenomena. Differentiability is all about the local structure being regular, right? Like differentiability only holds when you have this notion that around you there's a sufficiently, potentially small but finite region around you where you can effectively say, I live in a vector space. Everything is straight, and I can understand with my Cartesian mind where I am, right? That's what real differential geometry is about. Real as in real numbers. And so the analogy here, if we really take to heart the message that we are dealing with hypergraphs all the way down, and rewrite rules are the only thing that allow us to process information and to get from hypergraph substance to hypergraph substance, then I think that there is no real choice conceptually that charts will have to look like something like what's on the screen. It will have to look like that sort of setup. Anyway, I think that's a good output of this meeting. Definitely much more productive than last time.
There was a comment in the chat by Evangelos that infracalculus was easier.
Infracalculus was easier, yeah. That's interesting. We'll have to look at infracalculus again.
Could you derive infracalculus from infrageometry or vice versa?
No, I mean, these things are not well defined. So infracalculus is not a well defined thing. It's just that it was infracalculus was the emphasis on, I mean, they are one and the same thing. They're not really different. Infracalculus in some sense, it's just referring to the fact that, let me put it this way. Each chart, what an observer is doing on each chart, you could call infracalculus. It's not calculating in the mathematical sense. It's not performing operations in the mathematical sense. It's just letting the rules apply, and you're flowing with a multi-way system. And it's the causal properties of those multi-way systems that are going to give us some information eventually, right? So yeah, that's, by the way, that's in the sense in which I used infracalculus. So when I called something infracalculus before, I referred to this sort of rewrite based approach. But I think this is very good.
We had one request to comment on the first comment at the start of the chat. I don't know if you want to just take a second on that, and then we can close the session for the day and talk about what we might be doing tomorrow as well.
This is way too specific. It's talking about complex manifolds.
I think pop that in the Discord. Then we can just respond on that asynchronously. That might be the best way.
Absolutely, absolutely. Do that. And I want to give a shout out. Speaking of Discord, I want to give a shout out to Sam Rotke on our community. He's making some amazing contributions to the infrageometry discussion. He just posted earlier today some simulation of stochastic rewriting of unary edges to simulate diffusion in a graph. So some really cool stuff. Some really, really cool stuff. Head over to our Discord if you don't have the link.
Let me share my screen quickly. And do you want to post the link? I want to show this simulation.
Sure, I'll post it.
It's a really cool simulation. How am I going to do this now? Okay, I'll share. My whole screen's already sharing, so I'll just do this for the stream. But you can. We'll do this. So this is the simulation. It's pretty cool.
So you head over to this page on our website. You will see how to join, and just keep an eye out. Things are coming.
Great stuff. Okay, thanks so much for the session, guys. That was quite a cool exploration, charting some more of this land of infra we're investigating. Tomorrow we're going to be doing quantum paradoxes, which is this one particular one that's been stuck in the back of my head for quite a while, which hopefully Nick will be able to help elaborate on, which is the delayed choice quantum eraser experiment, and trying to think about why potentially it's not a paradox. I still think it's a paradox, but Nick's gonna try to convince me otherwise.
I'm not gonna resolve it, but we're gonna just dive in and see different interpretation of it, different how can I make it computable and all that.
Yeah.
Nice.
which is the intention of the institute. Can we make everything computable? That's like a meta quest for what we do here. Okay, great. Thanks so much, everyone. We'll catch you tomorrow.
Thank you, guys.
Cool.
See you later.